Right, girls, today's lesson is on piecewise or split functions. So the word split is just another word for piecewise functions. They're also known as split functions. And effectively what it is a graph with a collection of more than one function that is defined for different values of the domain. So in other words, we could have 2 different functions, 3 different functions, 4 different functions, however many different functions. And what is also important is to see how those functions connect each other. Remember that for a function to be a function, it cannot have more than one y value for the same x value. So that rule still has to be preserved. Okay, so looking at example 1, in the top left-hand corner, we have f of x equals, and then there are 5 different functions. X squared plus 2 for when x is greater than negative 1. For f of x is equal to 5 when x equals negative 1, f of x equals 3 when x is between negative 3 and negative 1, and f of x equals x plus 3 if x is between negative 5 and negative 3. Note where the domain values are included and excluded, and negative 2 if x is less than negative 5. So to start with, it might be useful to color code it. So for the first one, x squared plus 2 if x is greater than negative 1. So that's referring to this portion of the graph. Then if f of x is equal to 5 when x is equal to negative 1, that's just this value over here. Then f of x is equal to 3 if x is between negative 3 and negative 1, so that's this portion here. Notice the closed dot there because negative 3 is included, and the open dot there because negative 1 is excluded. Then we have f of x equals x plus 3 if x is between negative 5 and negative 3, not including, so that's that portion that I've highlighted in green. And lastly, f of x is equal to negative 2 if x is less than negative 5, so that's this portion here and carrying on to negative infinity. Okay, and then off at the other end of the graph, this graph carries on to positive infinity. So what's important for you to see is that there's actually a continuation of the graph from the left-hand side, y equals negative 2, then it changes to y is equal to x plus 3, then it changes to y is equal to 3, then there's that small dot where y is equal to 5, and then y is equal to x squared plus 2, and they continue in both directions. So that's effectively what a piecewise function is. So the left-hand side, the f of x, where it gives you all the algebraic equations, that mirrors onto the actual diagram where you can see each part of the graph shown. All right, a couple of important things that I want to highlight to you. If you look at this point that I'm circling now with pink, that is an included point at x equals negative 3. So therefore, this part has to be excluded. Otherwise, it would violate the rule for a function. Okay, the same thing goes here where x is equal to negative 1 and y is equal to 5. That point's included. But at this point where x is negative 1 and y is 3, that point is excluded. That's to preserve the function from the extreme left to the extreme right of the graph. So in other words, for every x value, there's only one possible y value that can be defined. All right, looking at the questions, question A asks us to evaluate f of 1. So the first thing we need to do is look at the graph and look where x equals 1 is. Because remember that these are all x values. F of 1 means x is the 1, and we're substituting that into f to get the y value. So 1 is here, and if we look, 1 is defined for the parabola y equals x squared plus 2. So all we need to do is substitute 1 in to that expression to see what the corresponding y value is. So we're then going to get 1 squared plus 2 into the parabola, which is 3. Right, question B asks us to evaluate f of 0. So again, we look at the graph, x is 0 there, and is also defined for the parabola. So we're going to substitute f of 0 into the parabola. Alright, and that gives us a value of 2. Right, for C, they're asking us for f of negative 1. So for f of negative 1, we look where negative 1 is, and we can see that negative 1 is on this perpendicular dotted line. It's not on the parabola because at that point, the graph is undefined. It's open. It's not continuous. So if we carry on further, we can see that there's a solid dot here for x is -1, and the y value there is 5. So there's no substitution or anything to do, but we can go straight to saying that it's equal to 5. We can also see that here in the definition, in that f of x is equal to 5 if x equals -1. At that point, notice it's not an inequality here, because it's only one dot. So at x equals -1, the only possible y value is 5. Right, D. They're asking in D for f of -2. So for -2, which is over here, we can see that it is on the straight line, y equals 3. So again, we can go straight to put in the answer of 3. Okay, for question E, they're asking us to evaluate f of -3. Right, so we look at -3. Now we can see x is -3 here. Now it's undefined at this point, which is where y is equal to 0, but it is defined at that point, which is the graph of y equals 3. And again, that is shown here in the definition, that f of x is equal to 3 if x is between -3, including -3, and -1. Now this is -3 itself, so that means we can go straight to the answer of 3. Okay, because that's the y value at that particular point. All right, f is asking for f of -4. So if we look at -4 on the x-axis, that brings us down to this function, which is the straight line y equals x plus 3. So that's what we're substituting -4 into. Right, so it'll be in x plus 3, which is -4 plus 3, which is then -1. Question G is asking us to evaluate f of -5. So again, we're going to look at -5. -5's over here. And now look at something interesting. -5, at -5, the y value is undefined. It's not included. And there's no other solid dot as there was here for when x is -3 and here for when x was -1. There's no other solid dot by -5. In that case, we then say that f of -5 is undefined. All right, the graph doesn't actually exist at that point. In fact, we can say there's a hole in the graph, and we're going to get to a bit more of that later, which is part of our continuity. And then lastly, H is asking us to define f of -6. And if we look where -6 is, we can see that -6 is on the line y equals -2. So that means it is -2. Example 2, consider f of x is equal to -2 if x is equal to -1, and f of x is equal to absolute x if x is between -1 and 1, and f of x equals 1 if x is greater than 1. So question A is asking you to sketch the function. Once we get to question B, they're asking you to evaluate all of these expressions like we did in example 1, but obviously according to your sketch. So it's important that your sketch is accurate. Right, so it's important that before we sketch, we got to look at what our key x changeover values are. So we see -1 there, that's when something changes. We see -1 again there, +1 here, and +1 there. So x equals -1 and +1 are our changeover values. So I'm going to put those in first. So -1 is there, and +1, let's say, is there. Okay, and just put a little neat light pencil dotted line so that you can work with that quite effectively once you sketch your function. Right, so let's look at the first part. Remember, it's a sketch, so we don't need to accurately measure. We need to just represent the correct intercepts, the correct values, etc. where we can. So the first part is -2 if x equals -1. So -1 is over here, and it's saying that if x is -1, then the y value is -2 at that point. So we're going to need a point somewhere here. Okay, so I'm going to put that in yellow, and it's a closed dot because -1 is included. That's where -2 is. All right, so I'm going to put -2 here on the y-axis so that we remember what that value is. Okay, so we've now dealt with this one. Right, now we're going to look at the next one. The absolute of x if negative 1 and if x is between negative 1 and positive 1. So you already know what the absolute of x looks like, so we can sketch that straight away. That's going to be like this, and it's going to be like that. Okay. Now what's important is to see what is included and what is excluded. So we can see that both the negative 1 and the positive 1 is excluded. Now this one definitely has to be excluded because we have the value here at the bottom where it's included. And remember, we can't have a solid there and a solid there. All right? But now this one is also excluded. And it's excluded because you'll see in the next graph, so we can tick this one off, we've done that one. In the next graph, the 1 is also excluded, so it'll stay on a yellow dot. The reason I'm highlighting that is because if this greater than sign was greater than or equal to, then this could still be solid because it's included for the straight line. Okay, so the straight line is now the last one. F of x equals 1 if x is greater than 1. So our straight line then is going to go like that, and it'll carry on to positive infinity because there are no further restrictions. Okay, so we've now dealt with all three, and we can now answer question B. Right, so question B says, if evaluate 1 f of 2. So we're going to substitute where 2 is. So look where 2 is on the diagram. You can, by the way, you can do this by looking here, and you can look at it by your diagram. And if you have time, it's a good idea to do both in case you've made a mistake in your diagram. So positive 2 is over here somewhere. So clearly we are on this line, this straight line, which is defined as f of x equals 1. So that one will then be 1. Okay, question 2. F of 1, we're going to look where 1 is. Now you can see that 1 is undefined. Okay, there's an open dot there, which means that our answer is undefined. So the graph is undefined at x equals 1. Then for question 3, f of 0, we're looking here at f of 0. So f of 0 is on the absolute function. So we're going to be substituting into the absolute. So it'll be the absolute of 0, which is actually just 0. Then for question 4, f of negative 1, we're looking at negative 1 here. Now negative 1 is undefined there in the absolute function, but it is defined at this point for negative 2. And again, that is shown over here, that if x is negative 2, then, sorry, if x is negative 1, then the y value is negative 2. All right, so we can go straight to putting that as an answer without having to show any calculations or working out. And lastly, for f of negative 2, now f of negative 2, can you see, doesn't exist. So negative 2 would be here somewhere. And there's no graph here at negative 2. The graph, in fact, stops at negative 1. So once again, f of negative 2, the graph is undefined. So another question they could ask here is, what is the domain of this function? So the domain, let's just look quickly. The smallest possible value that x can be is negative 1. All right? Because it is defined at negative 1 at this point. The graph's then continuous from negative 1 all the way to positive 1, and then immediately after positive 1, it's continuous again. So for the domain, the quickest way and the most effective way to write it is that x is greater than or equal to negative 1, but x cannot equal positive 1. Example 3, consider f of x is equal to the negative 1 if x is equal to negative 2. The absolute of x over x if negative 2 is less than x less than 2. And 2 if x is greater than or equal to 2. Question A is first to sketch the graph of f. Right, so again I'm going to look at what my main exchange points are. So we've got negative 2 again, positive 2 and positive 2. So at negative 2 and at positive 2 we've got a change over. Alright, so there's negative 2 and here's positive 2, and then let's just draw a neat little dotted line. And from there, we can then have a good idea of where the graphs are going to change over. Remember, it's just a sketch. Doesn't need to be measured. Doesn't need to be accurately plotted, as long as the correct turning points are in the right place, the graph's the right shape, and the intercepts are correct. Right, so the first one, f of x, we're going to sketch is equal to -1. Remember, these are y values, and these are the x values. So they're saying that y is -1 if x is equal to -2. So at -2 for x, at -1, we're going to have a solid dot. All right, so that's -1 on the y-axis. Now, for the second graph, the root of absolute of x over x if x is between -2 and 2. So for this one, I'm just going to take you down to a different page so that we can illustrate that properly. Right, so the graph of y equals absolute x over x. Remember that if x is greater than or equal to 0, then y equals x over x, which means that y equals 1. And if x is less than 0, then that means y is equal to negative x over x, which means that y is equal to -1. So these are the two parts of the graph that we're going to draw. Firstly, y is equal to 1, that's a horizontal line, if x is positive or equal to 0, and y is equal to -1 if x is less than 0 or negative. All right, so back to our graph here, we can then put those values on. Now, one thing that we've got to take care of before we do that, there's a variable in the denominator here, which is an implied restriction that x cannot equal 0. Okay, so that means immediately we've got an open dot here at x equals 0, sorry. Okay, so we can now sketch. We've already decided or worked out previously, I'm going to go back down there quickly, that y is equal to 1 if x is greater than 0, or y is -1 if x is less than 0. All right, so our first part of the graph is going to be here. Okay, so we're going to sketch that line. All right, so that was when x is less than 0. Going back to the pink here, if x is less than 0, then y is equal to -1, a horizontal line. And similarly, if x was greater than 0, then y was equal to +1. And again, there's an open dot here at +1. This is +1. There's an open dot that goes all the way to our next changeover point. All right. Now, at +2, I want you to just notice that it's not included for the absolute function, but it is included for the straight line function. So there's no need then for an open dot here. We can simply continue the function, and now the graph says that y is equal to 2 if x is greater than or equal to 2. Okay, so, sorry, just to clarify that, there should be an open dot here, but there is a closed dot here where x is equal to 2. All right, at that point, because now we're doing the third one where y is equal to 2 if x is greater than or equal to 2. So that means we now have a solid line going from the y value of 2 to positive infinity. Right, so let's go to our evaluations now. So for B, question 1, f of -2, we're going to look where -2 is. -2 is here. So clearly, f of -2 is defined at y equals -1. Right, next one, f of -1. So x equals -1 is somewhere here. So that's on this function, this straight line function, because we know it's between -2 and 0. Therefore, it has to lie on this straight line, which is defined at y equals -1. So that's also -1. Right, number 3, f of 0. Remember we said that x cannot equal 0. That's why at x equals 0, we've got an open dot there and we've got an open dot there. So the graph is not defined for the value of x equals 0. So therefore, f of 0 is undefined. Right, question 4, f of 1. +1 is somewhere here in between 0 and 2 on the x-axis, which means it's on this straight line, which is defined as y equals +1. Right, so f of 1 is equal to +1. Right, question 5, f of 2. We can see that 2 over here, here's x is equal to 2. It is undefined over here, but it is defined over here where the y value is 2. So we would therefore say that f of 2 is defined at x equals 2. Sorry, at y equals 2. And then lastly, f of 3, we're going to look at the value of 3, which would be here somewhere after 2, and clearly it is on this straight line where y is also equal to 2. So therefore f of 3 is defined at 2. Alright, example 4. If you didn't pause the video on the previous slide and continue exercise 2, then please do it now, because I'd rather that you finish that exercise before you continue with the rest of the lesson, because we're now combining the split functions as well as composite functions from the previous lesson. So example 4 is consider f of x is equal to x minus 1 if x is greater than 0, and x plus 1 if x is less than or equal to 0, and g of x is equal to x plus 3. Right, so they're first asking for question 1 of A, evaluate f of g of 2. So remember, g of 2 is now the inside function, so we need to substitute into g of 2, we're going to substitute 2 into the graph of g of x. So this is therefore going to become 2 plus 3 instead of x plus 3, okay, which is clearly f of 5. Now we've got to substitute 5 into x, but we've got to take careful note of the restriction. We're looking at 5. So does 5 fall in the restriction x is greater than 0 or x is less than or equal to 0? Clever girls, it falls into x is greater than 0. So therefore we're going to substitute 5 into this expression. Right, so 5 gets substituted into 5 minus 1, which equals 4. Right, for question 2, f of g of negative 4. So again, we're going to substitute negative 4 into g. There's only one expression for g, so there's no difficulty there as to where you've got to substitute it. So it's going to be f into negative 4 plus 3, which is then equal to f of negative 1. And then negative 1 again. We look at our restrictions, and negative 1 falls into this restriction where x is less than or equal to 0. So we're going to substitute it into x plus 1. Right, so it's going to be negative 1 plus 1, which is then equal to 0. Right, question 3 is asking for f of g of negative 3. Now remember from the previous lesson, this notation means exactly the same as what we did in question 1 and 2 of A, except that it looks a bit different. So if you want to rewrite it as f of g of negative 3, that is okay. Right, so negative 3 gets substituted into graph g, and that means we get negative 3 plus 3, which is 0. All right, so therefore we're substituting 0 now into graph f. So if we look at 0, it falls into this restriction where x is less than or equal to 0. That means we're putting it into this expression of x plus 1. All right, so therefore we're going to have not f, it's just going to be 0 plus 1, which is then equal to 1. Right, question 4. They are asking in question 4 for g of f of 2. Right, so now we have to start with f of 2. So we're doing it the other way around now. But because 2 is greater than 0, it means we're substituting it into this expression. All right, so we're going to leave the g, and we're substituting it into 2 minus 1. All right, so that becomes g of 1. And then we substitute g of 1 into the expression g, or we substitute x equals 1 into the expression of g, so it becomes 1 plus 3, which is then equal to 4. Okay, then question B has two parts. We're going to sketch the graph. Firstly, if y is equal to f of g of x. So effectively, this means that the graph is y is equal to f of g of x, which is x plus 3. All right, now that has its own implications, because remember there's a restriction now on f if the value of x is greater than 0 or less than 0. Okay, so that now means we can rewrite this in this format. It's either x plus 3 minus 1 if x plus 3 is greater than 0, or it's x plus 3 plus 1 if x plus 3 is less than or equal to 0. Okay, now why I've done that is because the value we're now substituting into f is x plus 3. So we're substituting into this x value here the value of x plus 3, and into that x value the value of x plus 3 over there, into the plus 1. All right, this simplifies. We can simplify this further. All right, so x plus 3 minus 1 is x plus 2 if x is greater than negative 3. Okay, just simplify the restriction a bit. And then for the second one, so I'm looking at this one now, we can simplify that line to read x plus 4 if x is less than or equal to negative 3. Right, so this is the line that we have to use now to sketch effectively. All right, x plus 2 if x is greater than negative 3, and x plus 4 if x is less than or equal to negative 3. So on our Cartesian plane, we have two x change values. So it changes at negative 3 and negative 3. So effectively just 1 for the two different conditions. Okay, so let's start by putting a negative 3 line, and we can then work with that. Right, so I'm going to start with this one, the first one. If x plus 2, it equals x plus 2 if x is greater than negative 3. Okay, and it's not including, that's important. So what you would need to do here is find your x and y intercepts of the function. Okay, so in the function, I'll work at the left here. If y is equal to x plus 2, we know that the y-intercept is positive 2, so we can mark that off straight away. All right, I'm going to do it in pink. So at positive 2 is our y-intercept. So for the x-intercept, you're going to let x equals 0. Sorry, let y equal 0. Okay, therefore x will equal negative 2. All right, so at negative 2 is our x-intercept. All right, and then you just need to link the function up. Now remember, this function is not defined for x equals negative 3. It's greater than or equal to negative 3. So it means then that we're going to link it, but make sure that we have an open dot at x equals negative 3. All right, so we're going to link it like this, and then have an open dot at the point x equals negative 3. Right, then the second graph, I'm going to use green for this one, is x plus 4. Now, if you want to sketch the x-intercept and the y-intercept, you can. We just then need to remember we've got to erase it. Okay, so let's look at x plus 4. So y equals x plus 4. We know that the y-intercept is 4. For the x-intercept, it's going to be x equals negative 4. All right, so, and we can tell that because if we let y equal 0, all right, then x equals negative 4. So I'm going to put both my intercepts in. So negative 4 is around here, and positive 4 is around there. So you can link them both. Okay, and obviously this extends into that direction. But now it's important to see that at x equals negative 3, we actually have a closed dot, because for this function, x is defined at negative 3. It's x is less than or equal to negative 3. But we now need to erase this portion of the graph so that our final function looks like that. And also, sorry, I didn't add this in, but this should be extending to positive infinity on that side because there's no further restriction. Right, for question 2 of B, they want us to sketch y equals g of f of x. So the other way around now, effectively. Right, so what this means is, effectively, that y is equal to g of f of x, which is the same as y is equal to f of x plus 3. Okay, so why I've done this is because effectively we're substituting f of x into the x part of 3. Okay, now why I haven't substituted f of x with these two yet is because there's two different ones, and we don't want to have this too complicated. So when there are two different ones in the split function, you simply use the f of x plus 3 first, and you substitute it in generic form into g of x. Okay, so that we have y equals f of x plus 3. Alright, so if we now expand that one, y equals f of x plus 3, based on your original instruction that was given, f of x plus 3 is equal to x minus 1 plus 3 if x is greater than 0. We're not changing these restrictions now because this is based on f, and we are substituting f of x into g of x. All right, and secondly, it's equal to x plus 1 plus 3 if x is less than or equal to 0. So just to recap why I've done that. Okay, look at the top over here. X minus 1 if x is greater than 0. But we've now substituted the x minus 1 into g. So that's why it's x minus 1 plus 3 if x is greater than 0. And then for the bottom one, it's x plus 1 if x is less than or equal to 0. But we've substituted the x plus 1 into g of x equals x plus 3 to get x plus 1 plus 3 if x is less than 0. So remember, when you're substituting the split function as the inner function, as we've done in 2, you do not change the restrictions. They stay as they were originally. Okay, so let's simplify this bracket now. So that becomes x minus 1 plus 3 is x plus 2 if x is greater than 0. And x plus 1 plus 3 is x plus 4 if x is less than or equal to 0. Sorry, that should also have an equal there. Right, and now we're ready to sketch. So I don't need to show you all the working out of the functions again because x plus 2 and x plus 4 were the same two functions that we used previously. We just have to make sure that we get the included and excluded x values correct. Right, so firstly, we're going to sketch the x plus 2 if x is greater than or equal to 0. So remember, that goes through 2 on the y-axis, and it'll have an open dot because x is 0 is not included. And it's going to go up at the gradient of 1, right? Because the m value is 1 in this case. Same, this graph, this pink graph there is the same one that we sketched in the previous exercise, except that it stops on the y-axis. It can't go to the left of the x-axis where the x values are negative. All right, and in the second part, x plus 4 if x is less than or equal to 0 is going to look like this. Now I'm just making the graph a little bit longer. All right, so x plus 4 would then come down like this. It'll have the same gradient because both of their m values are 1. It'll have the same gradient, except at 4, there's now a closed dot because x is allowed to equal 0. And obviously the x-intercept here is also negative 4. So that extends into a negative direction there.